ran across a statistic that was kind of interesting. The average adult male has about 3,000 square inches of surface area or skin on their body. And that makes for an interesting calculation. Suppose the pressure goes up, from the morning to the evening, and goes up just 1 inch in terms of mercury. Of course, that means about half a pound in terms of pounds per square inch, your pressure. Now, let's look at what that pressure does to the pressure you feel on your body. So at 30.5 inches, well, if you do the multiplication, you get about 44,940. Now the units here, units of inches squared, are going to cancel. You'll be left with units of pounds. So that's a force. Now let's make that cancellation a little bit more apparent here in this next one. As we do this multiplication, inches squared cancels out, and you're left with units of pounds again. If you subtract these two, you're going to get about 1,400 pounds of pressure. So mercury goes up 1 inch, all of a sudden they've dropped 3/4 of a ton of pressure on you. Of course, we don't notice it. It's just no big deal because it's distributed out throughout your body, but it's a lot of extra pressure. I mean, that's, weight of a small car maybe. Now, we're going to study what happens when those kind of things are looked at in fluids. Suppose you're submerging a plate in some fluid. So something like example number 1 here. You got this plate. How much pressure does it feel here as it's being submerged, a certain distance below the surface of the water or whatever medium this happens to be in? Well, to discuss that, we're going to need one thing here, and that's going to be Blaise Pascal. Let me give you kind of a brief history lesson before we really get into things. Blaise Pascal was an influential mathematician. He did a lot of work with, let's see, is that the right one? No, I don't think that is. Fractional exponents. No, not that one. Here we go. This is the one. He did a lot of work in mathematics, probability, etc. An early digital calculator, and was the first one to realize that vacuums are real and do exist. Most people know Blaise Pascal for something that we're going to use in section 8.1, which is Pascal's theorem, Pascal's triangle. You guys ever seen or heard of Pascal's triangle? Familiar with that one? Okay. We're going to use this in section 8.1. Wood's like, no, not me, man. All right. But it's kind of cool. If you take a look at what's happening here, hopefully you see the pattern, in terms of increasing the exponents on these binomials. But just look at the coefficients on the right-hand side. They form a nice, neat triangle. So the way you get one from the other, the next row down, is you add the 2 above it. So 1 and 2, that gives me the 3. Or 1 and 3 gives me the 4. 4 and 6 gives me the 10. And these are the coefficients of these terms in Pascal's triangle. So it's kind of handy. And like I said, we will use that in section 8.1. Now, that Pascal has his name attached to it is kind of strange because it's been around for a long, long time, even before Pascal. So here it is in Hebrew in 1834, going back even farther. And if you really want to go back and make sure that people understand that Pascal wasn't the first one to do it, let's look at it in Chinese from the year 1303. All right, so it's been around a long, long time. How Pascal got his name attached to it, don't know. Can't say. But what we're interested in right now is Pascal's Principle. And that's going to help us do some work with our fluid pressure. And it basically says this. The fluid force on an object is the same in any direction. So it's felt equally no matter which way you tilt this. If you tilt it sideways, face down, or vertical, that pressure is going to be the same in every direction. So, all right, that's good. Now what's going to mean for us is that when we're calculating pressure, the fluid pressure on a plate, we're going to have to multiply the weight density times the height. And that's going to help us calculate the fluid pressure.
Will the pressure be the same on the bottom side of
If as long as it's like infinitely thin, then yes. All right, but if it's a little thick, then there's going to be a little more pressure because of the change in depth. So it's a great question. All right. So looking back at example 1 here, let me get that straight. If you have a 12 square foot area for a plate, and the pressure is 374.4 pounds per square foot, well, that 12 times that pressure tells you the total pressure or the total force on that plate. Now that works good because this plate is horizontal with respect to the surface. But what if you start suspending it? What if it's vertical? So something like this. Then because the top edge of this is not quite as deep as the bottom edge, there's going to be unequal pressure. So what we're going to do is kind of like what we did for our work with centroids and some of our work with area and volumes, is we're going to take slices through our region and then add up what happens to all these slices. Now that delta y is your thickness. If you actually created a Riemann sum and added it up that way, you'd have a sum of all these thicknesses, including a delta y, basically your area. That delta y term is going to turn into a dy term when you pass through the limit. So how are we going to calculate the area, or excuse me, the pressure felt on these things? Well, here's kind of my spin on it. You can take a look at the book's spin on it. It's page 498. But the fluid force is really going to be an integral from, in terms of your y coordinates, the bottom to the top of your submerged plate. You're going to have this constant here, which will be given to you. That's going to be the weight density. Then you're going to have a function which is going to be the distance to the surface times the area of your one slice. Now the area of your one slice is where our work's going to come in. It's going to be the width of that slice times the thickness, which is always going to be dy. So that's in general terms what you're going to be looking at when you try and find the fluid force on one slice. And then add up the fluid force for all slices with the integration. We're going to start with kind of a friendly one, and that's going to be problem number 16. So problem 16, I say it's a friendly one. It's a friendly one because this plate has a uniform width. All right, the plate doesn't vary in width from top to bottom. It's just a nice constant width of 1. So let me draw that, and then we'll work on calculating the pressure on this. Now this is submerged in water. Now the book gives you that the weight density of water is 9,800 newtons per cubic meter. So problem number 16. So W is 9,800 newtons per cubic meter. Now I'm going to assume all these measurements are done in terms of meters. So first things first, we got the surface of our water. And then 1 meter down, we have our plate. And our plate's a total of, what, 5 meters tall? Is it 5 or 3? 5. And it's also 1 inch or 1 meter wide. So that's the dimensions of our plate. So let's see if we can't figure out how much force is being felt on that plate. Let's see. So we're gonna follow suit with what we've done with a lot of these. Let me make sure this is clear. That width is 1 meter, and this distance is a total of 5 meters. It would probably help us out if we gave ourselves some coordinates. So at least on this first one, I'm just going to start by putting the surface right up here at 0, 0. So that's our frame of reference. What coordinates does it give me down here then? 0, -1. All right, 0, -1. And we're going to need one more coordinate, but let me draw our slice through this region first. So that's going to be this right here. Okay. So a little slice. We're going to want the area of that one slice. And eventually we're going to calculate the area, the force on that one plate. So let's work that over here. Force on one plate. So the force on one plate is really going to be a product of several things. So the force on one plate is going to equal rho, which is your density, times the depth, times the area of one slice. Now the force they've already given us, that's 9,800 newtons per cubic meter. I'm not going to actually put in units there. Now the depth, that's going to be how far below the surface our little slice is. So if I go all the way down here to that slice, what coordinates can I put here? Uh, 0 and y. I'm just leaving it at 0, y. Don't try and play with negatives. The negatives will come out when we deal with our limits of integration. So the depth of our slice is going to be the top minus the bottom. So it's going to be 0 minus y or negative y. Now we're getting a negative y because we're below the surface of the water. If you redo this problem and you put 0, 0 here, then you're probably not going to get this negative y term. It's okay. It's not a big deal. Nothing wrong with having a negative there. Finally, we need the area of the one slice. Area of one slice. Well, it's going to be the thickness times the height here. The height of our slice. What's the height of our slice? dy. So the thickness times the slice times the width here is going to be 1 times dy, or just dy for the area of that one slice. So I've got all three things now, all three things that I need. I've got my density right here. I've got the depth right here. And I got the area of that one slice. So that would be here. Let's put that all together. That'll give us the force on one plate. So that's going to be negative 9,800 y dy. Now that's the force on one slice. I need the force on all such slices. And you know what? I think I'm going to need one more coordinate from you. And that's going to be down here at the bottom. What's the coordinates down here? Good, 0, -6. All right, because you're a total of 6 meters below the surface. So if I want to try and find the fluid force on this, then we'll integrate -9800 y dy. What should my limits of integration be? Good. -6 to -1 from top to bottom, or I mean from bottom to top. Are we okay with the setup on this? Looking good, Andrew? Okay. All right. The rest of it, I'm hoping, is not really a big deal. You can factor out the -9800. The integral of y is going to be y squared over 2 between -6 and -1. So -9800 times square that's going to be 1/2 minus 1/36. Oops, sorry, not 1/36. Sorry, scratch that. -9800. Let's see. So the first one is going to be 1/2. The second one's going to be what? -18. So 1/2, and then yeah, 18. Huh? Oh, good question, because that's the top of the plate. All right. You don't want to go all the way to the surface because the plate only runs up to here. All right. Thank you. Okay, so let's give me -9800 times -17.5. Someone do that out for me? Let's see. So 9800. Getting 171,500. What units are going to be left? If you cross out, you cancel out meters cubed, what units are left? Newtons. Just newtons, yeah. Let's see here. Yeah. Okay, 171,500 newtons. We okay with that one? Okay so far? Anish? Say again? Oh, the depth? Because the depth is the distance from here to here, and I measured that as being this one, that y coordinate minus this y coordinate. So top minus bottom gives you a depth of 0 minus y, which is -y. Had we set this up differently, if I put 0, 0 here, then up here I would have had a 6. Then my depth would have been 6 minus y. So it just depends on how you set up your coordinates. We could have put 0, 0 here. So there's a lot of different ways you could have set this up. But when you're calculating this distance right here, so let me see if I can. That's your depth. It's the distance below the surface, and it's going to be the difference in those two coordinates. So you're just going to subtract them. And the way we set it up, we just happen to get a -y. What would have been wrong, suppose you missed that negative here, then we would end up with a -171,500 newtons. Would that have said that there's something wrong? Probably, hopefully, because then all of a sudden you got a negative force. So that would be bad. All right. Good question. Anything else on number 16 here? Let's try some more. And what's going to happen is that the figures are going to change in shape. This one was a nice one because the figure was a constant width all the way down. You're not always going to be quite so lucky. So let's try a couple more. Let's try problem number 10. Problem number 10, they give you a semicircle. So let's draw ourselves a nice little semicircle.
That was easy.
You knew that was coming, right? All right. So semicircle, radius 2. So right there. Let's put, for convenience, I would strongly suggest that you put the origin right here. So 0, 0 is your origin. Now the edge of this is going to be right at the surface. Actually, you know what? They say that this is the edge of a tank and it's full of water. We'll put the coordinate 0, 0 here because that's going to give us an easy coordinate or an easy expression for the equation of a circle here. So if that's 0, 0, this is going to be 2 and 0, and of course negative 2 and 0. We're not going to need that too much. The other coordinate that I guess I'll deal with, maybe there's two of them. One of them's down here. What's the coordinate down here? 0, negative 2. And as before, we're going to draw a little slice through this region. So let's take a little dy slice. dy, and I'll give that coordinates of 0 and y. Just to help you out here, the equation of a circle in this case is going to be x squared plus y squared equals 2 squared. So it's definitely something that we're going to want and need to know. Let's work on finding the force here. So the force, as before, is going to be the density times the depth times the area of one slice. This is kind of a geometric approach. Not putting myself in the same category by any means, but Einstein did a lot of his thinking in geometry. And later on, when he could no longer picture things, he struggled a little bit more. So the density of water, let's see, are we working in feet or... density of water is 62 pounds per cubic foot. 62.4. Let's see this. That's density. That's pounds per cubic foot. We want pressure though. No, they're using 62.4 as well. Yeah, the weight density. All right, so 62.4. The depth is going to be the top minus the bottom. So 0 minus y or minus y again. The one problem that we're going to run into, and I guess I need some more coordinates here, is the area of that one slice. So the area of one slice is going to be the distance between these two here. Now, I don't have it really written here, so let's come up with it now. What are the coordinates at this point, or what coordinate could I put there? Yeah, x and y. And over here, it'd be negative x and y. Well, y is going to have a negative value, but I'm not going to write the negative there. Yeah. So the area of one slice is really the width times the thickness. Now the thickness here is going to be our dy. What's the width of this? Well, the width is going to be the difference in the x coordinates. So it's going to be x minus negative x, or better yet, just 2x. But are we going to have a problem using that as part of our integral? Yes. What's the problem? What are we going to run to that's a little bit of an issue there for us? Yeah, we need to put it in terms of y. And that's why I wanted to use 0, 0 as the coordinates here, because it's going to make for an easier equation. If you solve for y, up here you're going to get y equals plus or minus the square root of y, of 4 minus x squared. Okay. So we can replace that. Actually, you know what? I should do it the other way around. X equals plus or minus the square root of 4 minus y squared. There we go. All right. We can replace x here with the square root. 2 square roots of 4 minus y squared dy. Now we're in good shape. Now we have everything we need. We've got density. We've got the depth, and we've got the area of one slice. So I think we're in good shape here. Area of one slice. Let's put that together and find the volume, excuse me, not the volume, but the force on this plate. All right, so it's going to be an integral. 62.4, let's just put that right outside. 62.4 of negative y times the square root of 4 minus y squared dy. Now I need my limits of integration. Let's see, there's a 2 here as well. So let's see, where can I squeeze it in? 2 times that. So I'll bring that out as a constant, so 124.8. And let's also take out the negative as well. So it's going to be y times the square root of 4 minus y squared dy. I still need my limits of integration. Where am I going to integrate from and to? Start with the lower limit. What's the lower limit of integration? Negative 2 up to 0. Negative 2 to 0. Actually, it wouldn't have hurt to leave the negative in here, but that's all right. How am I going to integrate this? And we'll actually do it all out. Sometimes we take the time to do it, sometimes we don't. This one I just kind of want to remind you of how to do this one. How would you integrate something like this? U substitution. The key in the U substitution, and we'll practice this more in 8.1, is if you see part of the integral is a derivative of another part. When you differentiate a term in y squared, you're going to get a y to the first term. So that's very suggestive of a U substitution right here. We're going to let u equal 4 minus y squared. Du by dy is negative 2y, or du equals negative 2y dy. Thank you. personally, when I change variables in a definite integral, I like to change the units as well. So let's plug in u of negative 2. It's going to be 4 minus negative 2 squared, which is 0. And u of 0, which is going to be 4 minus 0 squared, which is 4. Probably one more thing that I want to do here, which is solve for what I have in the integral, which is going to be my y dy term. So that's negative 1/2 du equals y dy. And now I think I've got everything lined up so that I can do my substitution directly. I've got a y dy term, which is right there. I've got my u term right there. And I got my new limits of integration right here. Let's substitute in everything and see if we can't make this all work. So it's going to be negative 124.8 times the integral from 0 to 4. Instead of a y dy, I'm going to put in a minus 1/2 du. And then I'll have the square root of u. Looking better. The 1/2 and the 124 can simplify. A negative times a negative is also going to simplify. That's going to bring me back down to 62.4 times the integral from 0 to 4 of u to the 1/2 du. So just rewriting it with rational exponents. That way we can integrate it. 62.4 between 0 and 4. When you integrate this, you're going to add 1 to the exponent. 3/2 divided by 3/2. Dividing by 3/2 is the same thing as multiplying by its reciprocal. So this times 2/3 puts us back up to 124.8 over 3 times 4 to the 3/2 minus 0 to the 3/2. I don't know as though that's really going to simplify to anything really special. Get about 332.8 pounds. So I think what I get, 332.8 pounds. Whew. Okay. Yes. No, I don't think so, because you've got a no, because that would need to be in like a denominator, right? Yeah. So no. It also feels like it'd be making it much harder. Yeah, but good eye that it does look very close to an inverse secant. Yeah. Anything else on this one? Okay. Two more. Let's see. Maybe we should do one more. Boy. How are you doing? Do you want two more or one more? One more? Two? Two? All right. The majority goes with two. All right, let's go with two. Get your money's worth. That's right, man. Get your money's worth. Cool. I'm all for it. Problem 20. So another one where we've got a plate submerged. This time, the figure here is going to be the edge of a concrete form. So let me draw that for us. It's going to be a triangle. It's also going to mean we're going to have a different weight density. So across the top, we've got a distance of 5. So I'm going to put 0, 0 here. And if this distance is a total of 5, that puts this at 5, 0. Now the depth of this down to that point is 3 feet. So if this distance is 3 feet, what's the coordinate of that point? Close. 5, not 3, but negative 3. 5, negative 3. So concrete is going to weigh a lot more. It's going to have a much higher weight density than water. They say 140.7 pounds per cubic foot. So 140.7 pounds per cubic foot. That's our density. We're going to need to find the force on one plate. So let me draw our plate. Your plate's always going to come from a horizontal slice through your region. That's going to make it always a dy slice. I'm trying to be consistent with these slices. We've used them a lot so far in this course. So dy. We want to find the force on one plate. So that force is going to be the density times the depth times the area of one slice. And we already know part of that. We already know the density, so we're good there. Let's put some coordinates here on our figure. What coordinate could I put here? Five comma y. Excellent. Thank you. 5 comma y. Dawood, something about that? Okay, cool. All right. Let's work on the depth. So Rand, the depth is going to be the distance between these 2 points. So what's the depth going to be? Zero minus y, or just negative y. Top minus bottom. Good. Last but not least, we're going to need the area of that one slice. So that's that last piece of the puzzle here. Area of one slice. Well, let's see. That's 5 and y. I don't really know what this coordinate is, do I? It's just, I don't know, something and something else, x and y. But I can get a better handle on it because I know, or I can come up with the equation of a line for this line right here. In fact, that's going to be pretty easy. Y equals mx plus b is the general form of the equation of the line. But one of those parameters we can tell without much fuss, right? If your line runs right through the origin, what's it? B is gone. So it's just y equals mx. All right, well, that's even better. And what's m in this? M is your slope, which is the rise over the run. So if I start out here, how much of a rise is there in moving towards this point? The rise is -3, and the run is 5. So, well done, Todd. -3 over 5x is as your general term, or as your general equation here. Let me call this point x and y. Actually, I guess I could call that, x and y is fine. But what we need is we need this distance here. How far is it from this point to this point? Because I want to figure out the area of that little pink plate. So the area is going to be 5 minus x times the thickness, which is dy. Can you spot now why I needed to come up with the equation? It's not going to be good enough to do 5 minus x. Why not? Thanks, Ronnie. You need it in terms of y. So you've got this dy term over here. That's telling you, in fact, you got this as y. That's in terms of y. This needs to be in terms of y. So, Vang, how am I going to come up with an expression in terms of y? What should I do? How about this right over here? You came up with that equation? Yeah. Yeah, if you multiply both sides by the reciprocal of negative 3/5, that is negative 5/3, we get an expression for x. So just like the last problem, you had to come up with an equation that you can use so that you can substitute in for x. So the area is going to be 5 minus negative 5/3 y dy. And we can clean that up if you want a little bit. It's 5 plus 5/3 y dy. So the hard part there is just setting up the equation. Trevon, with me? Okay, good. If we put all this together, we can get the force on that one plate. Now, what we'll have to do is add up the force for all such plates, but we do that by integrating. So the force on one plate is going to be 140.7 times the area, times the depth, which is minus y, times the area of one slice, which is this one right here, 5 plus 5/3 y dy. That's the heavy lifting in all this one. It's coming up with that one expression. Oftentimes when I grade you, what I'll do is I'll solve the problem myself and I'll set up specific little, checkpoints. All right, you should have this expression. You should have solved for an equation for y, so points for both of those. You should integrate it and set up the correct limits of integration. So let's see if we can do that. The integral is going to be, I'm just going to reorder this a little bit, negative 140.7 times y times 5 plus 5/3 y dy. Where are my limits of integration? Good. Yeah, -3 to 0 from bottom to top. So -3 to 0. I don't think it's really worth it to spend all our time doing this out by hand, so let's just jump to the happy ending. 1055.25. What units are going to go with this? Pounds. Good. Pounds. So it's a lot of force for a relatively small area. The area is like 7.5 square feet, so a lot of force. Any comments or thoughts on problem 20? Something that maybe I went over a little too fast you'd like to see one more time? Yes? What's that? That's a good question. When you're substituting in here, you're going to end up with an area, which is going to be in units of feet squared, and then some more, which is going to be feet cubed, and that's going to cancel out with the feet cubed in the density. All right, good question. Trayvon?
Yeah, when you were finding out the area of the one slice, it had to be like side was it had to be 5 minus x, it couldn't be 3 minus y.
3 minus y would be the difference here. That'd be your vertical height. That's more like the distance between the bottom of this and here. Actually, 3 minus y would be a distance between a point 3 feet above the surface and here. But we wanted to find this distance here. Now, your horizontal distance, and it's a great question. When you're finding your horizontal distances, it's always going to be the difference of the x coordinates. So the right coordinate minus the left coordinate. So in this case, 5 minus x, that's going to give you your horizontal distances. If I needed a vertical distance, and we did in this one, then what did we do? We subtracted the y coordinates. So 0 minus y, that gave you your vertical distance. So top minus bottom, or right minus left to get your distances. Okay? So appreciate the question. Any other ones? These help me out. They help you out. So last one, problem number 24. Let me give you kind of a little break for a moment from the action with a little foreshadowing here. So you see foreshadowing in good authors, etc. I'm going to do a little foreshadowing here. So what I have here is an even function. It's actually probably like 1 minus cosine of x or something like that. Now, the thing about an even function is when you're integrating an even function over a symmetric interval, well, you're essentially finding these areas, right? The area between the x-axis and our function. Well, if we have an even function, and by an even function I mean it's symmetric with respect to the y-axis, then you got a little thing that you can do here. This area and this area are going to be the same. So when you integrate that even function, you can, instead of going from negative a to a, you can do twice, half of that, twice from 0 to a. So, all right, that's nice. What if you had an odd function? Now, an odd function looks a lot different, and it's tough to spot odd functions. You'll see them as cube roots, sines, etc. But you have an odd function, then when you find this area, say you get some value, call it V1 is the area of this over here. When you integrate to the left of 0 over here, you're going to get the negative of that. So that if you integrate it from here to here, basically you're going to be adding up this area plus this area, except this area gets the sign coming from being below the x-axis. So what's going to happen when you integrate the whole odd function over this symmetric interval from negative a to a? You get 0. Right? So it's the odd function rule. It's a really nice rule if you can spot either of these. Now, when should you look for them? Well, look for them if you have a symmetric interval. Integrating from negative a to a, then start looking for the odd or even function rule. You're not always going to find it. Or maybe sometimes you'll overlook it, and that's okay. But of course, if you overlook it in this case, you're going to do a lot of work literally for nothing. All right? Because you're going to get 0 when it's all said and done. But it's all right. You don't have to find that one. Okay, so let's do our last one here. Problem number 24. All right. So this time we're going to submerge a window 5 feet below the surface. It's 2 feet in diameter, and yeah, we're going to deal with water. Assume it's water and feet. Okay, so let's draw this. slash add coin. This is painful. Sorry. That's too painful. All right, let's try it again. You got a quarter? Actually, when you look at a quarter, you got a nickel? Nothing? Nickel? That's even better because it's smooth edges. When you feel the edges of a quarter, you're actually touching something that Newton helped establish. Newton for a time was warden of the Royal Mint, and it was a time during which England was really afraid of getting taken over by France. So it was important to have good currency to be able to pay off your troops. Well, the problem is people would take a coin. Back then it was all silver, not like the silver copper things we have now. It was all silver, and they'd shave off a little bit, or they'd clip a little bit, and then they'd pass it off, and then essentially they made money. All those clippings and shavings, that's their profit, right? Well, that debases the coin, and you can't use it. So his idea was to put those edges on the coin that you see on a quarter, so that if somebody shaved it, it'd be really apparent. You go, no, give me a real one. Give me a better one. So, hand of Newton is touching yours. How about that? Cool. All right, so let's see here. We've got this circle. This circle is 2 feet wide, and this distance here is 5 feet. So this is problem number 24. And like I said, the diameter of this would be 4, the radius is 2. The question is, where do you want to put the origin? We need to decide something so that we get an equation that we can set up for this circle. Personally, I think the easiest thing to do would be to set the origin right here at 0, 0. So if we made that 0, 0, then this would be 0, 2. If that's 5 feet, what would the coordinate up here be? 0, 7. And down here at 0, negative 2. Of course, that's 0, 0. A circle of radius 2 is going to have the equation x squared plus y squared equals 2 squared. So we'll just put that aside for later. And let's go back to something familiar, the force on one plate. So I'm assuming we're going to work in water. So the weight density of water is known. So we have the depth, it's going to be density times the depth times the area of one slice. Density is 62.4 pounds per cubic foot. The area of one slice. So it's going to be, let's see, do the depth first. So because our origin is here, it's going to be a little bit different expression for the depth. Pounds per, yeah, I did. Pounds per, how about pounds per foot cubed? Thank you. Foot cubed, yes. Oh, thank you. Yeah, pounds. Make that. All right. Operator error and multiple levels. There we go. Pounds per foot cubed. Thank you. The depth. Well, let me draw in our slice first. So, slice. And let's put it down here. I'm going to give that coordinates of 0 and y. And on the side here that's going to have coordinates of x and y and negative x and y. So the depth is the same thing as before. Try and come up with an expression for the depth. Try and come up with an expression for the depth, and then if you're really good, try and find the area of one slice. As far as the depth is concerned, the depth is the difference between this point, the surface, and this point where your slice is. Which coordinates should I be subtracting to find that depth? The y coordinates. So 7 minus y, that's your depth. Now I need the area of one slice. And some of this is going to look familiar. The thickness of this slice is dy. But then I need the horizontal distance. What's the distance between x and negative x? What's the distance horizontally here? 2x. 2x times dy. Well, we're running into the same problem that we ran into a little while ago. X is going to equal the square root of 4 minus y squared. 2 square root of 4 minus y squared dy. Yes? Mostly because we can. Yeah. But the distance is, you know, it's going to be a positive distance, so we're okay there. Yeah. All right. Let's put all this together here. I want to find the total force here. So the force is going to be 62.4 times the depth, which is something other than just a minus y for a change, times the area of one slice, which is 2 square roots of 4 minus y squared dy. Let me clean that up a little further. 2 times 62.4 is 124.8. So 124.8 times the integral of 7 minus y times the square root of 4 minus y squared dy. Tricky question here for you. What are the limits of integration? Nope. Remember, you have to, the limits of integration are going to come from where the slice can vary. Now, you're varying with respect to y, so in the y direction, what are the limits for y? Negative 2 to 2. Okay. Let me pause, because the setup is the tough part. So getting this thing set up is where you're really going to be challenged. The rest of it is going to be really cool. So the part that's going to be amazed. You're going to think, wow, you integrated that without integrating. That's our goal. Integration without integration. Like that idea? You can't really do it with a dx slice because the dx slice, the force is going to be changing throughout the length of it, right? Because the force is going to be changing at the top. It's not going to be the same as it is on the bottom. It's going to vary. So this dy slice is some imaginary thickness, which is arbitrarily thin is really what it is. So there's really no top and bottom to this slice. I kind of show it that way. But this doesn't have, it's going to have the same pressure on the top as it on the bottom because it's arbitrarily thin. That's not going to be true if you took a dx slice. There's going to be a little bit more pressure on the bottom than there is on the top. If you've ever heard somebody discuss falling into a black hole, there's something called, you get stretched like spaghetti. This is what happens because as you fall in, there's a little bit more tug of gravity as you're falling towards it on your feet than it is on your head. And eventually that force gets magnified, and as you fall in, you get stretched like spaghetti. So probably not too fun to fall into a black hole. Although your friends could watch you forever because you would just never really approach, you'd never actually get there. It looked like you're always getting closer to the horizon of the black hole. Anyways, back to this stuff. Let's see if we can't integrate this without integrating. So what I'm going to do is I'm going to distribute this term to both of these and then break it up into two integrals. So it's going to be 124.8 times negative 2 to 2 of 7 times the square root of 4 minus y squared dy minus 124.8. The minus, I'm just going to factor out negative 2 to 2 of y times the square root of 4 minus y squared dy. Great. We're almost done. Can anyone see a nice easy simplification here? Which one? Or both? Hopefully not both, right? If both equal 0, we'd be in trouble. There'd be no pressure at all on this plate that's submerged. All right. One of them does equal 0. So which one? Second one. The second one is an odd function. The first one's an even function. This is 0 by your odd function rule. Odd function rule. Yay. Wow. Hey, I like that.
That was easy.
Yeah, perfect. How about the other one? Let me take the 7 out of here. So 7 times that, that's going to be 898.8. 898.8. Integral from negative 2 to 2 of the square root of 4 minus y squared dy. Now let's think about what that looks like. Not a sphere, but a semicircle, right? So basically, what you've got there is you're trying to find the area of a semicircle. So, I didn't draw it quite perfect here, but there we go. So you're trying to find the area of a semicircle. So this is y equals the square root of 4 minus x squared. All right, I changed things up a little bit just out of my convenience. But you're trying to find that area. Well, we should know that, right? Do we need to use calculus to find the area of a semicircle? Not when you know the radius, no. So that area, we're going to have 898.8 times 1/2 pi times 2 squared. So basically, one of the 2's is going to cancel out. You have 2 times that, so 1,797.6 pounds of force. So there you go. Integrated it without integrating. Yes? 7 times 124. I'm hoping my math is right on that one. I'm thinking I'm good. Donnie would spot it in a minute. Yes? That's a little bit more skill. I mean, you could take a look at it graphically. I mean, one thing that starts to pique your interest is you've got a symmetric interval. All right, so you can look for that, symmetric intervals, then you start thinking, all right, maybe there's something going on. If you looked at the graph, you'd see that it has the shape that I outlined earlier, that to the left of the origin, you've got an area under the graph, and to the right, you've got an area above the graph. Basically, what happens in an odd function is that no matter where you are on the graph, if you draw a line through the origin, So let me do that here. Draw a line through the origin. You're going to find points that are on opposite sides. So if you have x and y here, you'll have minus x and minus y here. So say 2 and 3, negative 2 and negative 3. That'll be true for all your odd functions. The formal test is if this is true. If f of negative x equals negative f of x. If that's true, then it's an odd function. That's a formal test. I don't know how much you want to slow down to do that. I mean, some of your odd functions would be x to an odd power, tangent of x, sine of x. Those are a couple of good examples of odd functions. So if you're pretty confident, then you can go with it. But you know what? If you're not, then just do it out. And if it was, oh well. If it's not, then you're in better shape. Yeah. All right. I think that's good enough for this section. Yeah. There should be a pi in here. Pi. Thank you. So you should have the pi in there. So probably close to 6,000 pounds altogether. Yes. For homework, try 7 through 21 and 24B. That's section 7.7.